Welcome to all of you. Today we discuss about fixed point representation with an example from numerical analysis. And this is the numerical analysis for chemistry semester 3, paper B.Sc 3. What do you mean by fixed point representation? Why is it convenient in most cases? What is fixed point representation? This is a method of storing real numbers in a computer where the position of the radix, that is binary or decimal point, is set at a fixed predetermined location within the sequence of digits. And hence, the method takes the name fixed point. Actually, this binary point fixed at certain position. And this means a fixed number of bits are allocated for the integer part and a fixed number for the fractional part. The computer treats the number as an integer and the programmer implicitly handles the scaling factor and the location of the point. For a fixed point number in binary system, the bit, most significant bit MSB, that is the leftmost bit, is used as a sign bit. For positive number, sign bit is 0, and for negative number, value of sign bit is 1. Now, number actually for negative number can be represented in one of the following ways: either sign magnitude representation, signed one's complement representation, signed two's complement representation. When we deal with positive numbers, then it's standard unsigned binary form with a leading 0 to indicate they are positive, and negative numbers are represented using one of this complement method, ones or two's complement method, primarily used the negative form of a number in binary system. There are several drawbacks in sign magnitude and one's complement representation for a negative number. And a modern computer system, we use actually two's complement representation for the negative numbers. Consider uh, an example. This is an example. Represent the following decimal number in 16-bit Q8.8 fixed point binary form. Number 1, 64.75, and number 2, minus 64.75. Actually, Q8.8 means this 16-bit fixed point binary number where the rightmost 8-bit for fractional parts and 7-bit for integer parts and 1 bit for sign bit. Now, first we find the value of 64.75 to the base 10 in 16-bit Q8.8 fixed point binary form. For that, first we convert this number in binary representation. So 64 to the base 10, actually this is the for 8-bit. This first 0 represents the sign, this positive, so this 0, and next convert 0.75 to the base 10 in binary form. So we get 64.75 to the base 10 equal to this 0, 1, 0, 0, and this 0.11000000 to the base 2. And this is the binary point. This is the binary point. The right part, there are 8 bits, and from the left part of this binary point is 8 bit, of which this uh, leftmost bit, most significant bit, MSB, is 0. So this is the positive number. This 16-bit signed magnitude fixed point binary representation is given by sign bit 0, integer part. This is the integer part 100, and this 000, and for fractional part 8-bit is this. Hence, this is the 8-bit sign magnitude representation. This fixed point representation is given by this. Next, we find negative of this number, minus 64.75 to the base 10 in 16-bit Q8.8 fixed point binary form. First, we find the value of 64.75 in 16-bit fixed point sign magnitude. Already we have done this. So 64.75 to the base 10 equal to this. Then we find its ones complement form, including the sign bit, by interchanging 0 to 1 and vice versa. So replacing 0 by 1 and 1 by 0, we get this is the one complements form. Actually, this is the negative of this number. This represents the ones complement form. Next, we add 1 to the rightmost bit. This is the rightmost bit, this 1. The least significant bit, LSB. Add 1, this, so 1 plus 1 is 0, carry 1, this 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, and this, and this is the 1. And this is the 2's complement form of this number. Actually, this represents the negative of this number, negative minus 64.75 to the base 10 in 2's complement form is this. So in 2's complement fixed point binary representation is this sign bit, this 1. Actually, this negative, for this negative, this 1, integer part is this 7-bit, and this fractional part is this. And this is the minus of this. Now we can verify this number 2's complement form, fixed point binary form. This convert to the original decimal form. So the leftmost bit, actually this is the leftmost bit is the most significant bit is the 1. Actually, this value of this 1 is minus 2 to the power 7. This is the minus 2 to the power 7, or minus 128 for this. Actually, this is the 0 from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. Sorry, this is the 2 to the power 0, 1, 2, 3, 4, 5, 6. And this is the 7. So this is the 2 to the power 7. So this is the negative, so this is minus. The value of the leftmost bit for bit 1 has weight 1 minus 128. And for integer part, that's the 15th place to 9th place bit. So this 0 to 1 for this part. This is the 0 into 2 to the power 6 plus 1 into 2 to the power 5. This is the 2 to the power 4, 0, or 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. 0, 1, 2, 3, 4, 5, 6. So this is the value is 63 in decimal form. And for fractional part, so this is the from the 8th bit to this first bit, this 0. So this 2 to the power 0 into 2 to the power minus 1, 1 into 2 to the power minus 2, and so on. This is the value 0.25 in decimal form. Hence, this minus 128 plus 63 plus 0.25 is equal to minus 64.75. Now, we can verify this from this Q format converter and calculator. This word size m plus n. This n means the fractional bits, this 8, and remaining 8 bits, 1 bits for sign and 7 bit for integer part. Now we here put the fractional value 64.75, 64.75, 64.75, sorry, 75. Change this to binary. So 64.75, 64.75, this is the 0 1, this 0 0 1 1 0 0. This is the binary form 64.75. This is the 0 1, 64.75 is this 0 1, and this 6 zeros 1 1, and next 6 zeros, and this is the 0 1, 6 zeros 1 1, then 6 0. We put here uh, minus here, so 64 point minus 64.75 in decimal form. So value of this is 1 0 1 1 1 1 1 1 0 1, and this is this, and this is the fixed point binary representation in q 8.8 bit, q 8.8 bit, actually 8 fractional part, and this 8 for integer part, including one sign bit, and this is the minus 64.75. Next, next part, second part, why fixed point representation is convenient in most cases. The fixed point representation is used for better computational efficiency, lower hardware cost, and predictable precision within a defined range. First one, performance and speed. This performance is better performance for arithmetic logical unit. Number two, lower power consumption and hardware cost. Number three, predictability and determinism and memory efficiency and suitability for specific ranges. This is the facility of this fixed point representation over this. And next, uh, in the note 2, drawbacks of sign magnitude and ones complement representation. The extra part, actually sign magnitude and ones complement representation have several drawbacks, and for represent negative number, actually here the dual representation of 0. Both systems suffers from the having two different binary pattern for the number 0. In sign magnitude form, 8-bit number, this represents plus 0, and this represents 1 0 0, this is the minus 0. And in one's complement form, this represents plus 0, while this 1 1 1 1 represents minus 0. And this ambiguity wastes the representable value and complicates the equality checks, as the hardware must check for two different patterns to determine if a result is 0. And the other complexities, the standard arithmetic operations are more difficult to implement in this format compared to 2's complement. The sign magnitude, the CPU cannot treat the sign bit like a normal value. And for 1's complement, while it simplifies subtraction by flipping bits, it actually 0 to 1 and 1 to 0, replacing this. And this, if an addition result in a carryout from the most significant bit, that carry must be added back to the least significant bit to get the correct result, requiring additional clock cycles or more complex adder hardware. And numerical ranges, this for 8-bit ranges, sign magnitude and one's complement both cover minus 27 to 127 to plus 127. But the 2's complement ranges minus 128 to plus 127, because it has only 1 0, allowing the extra bit pattern to represent an additional negative number. So, so in the modern computer system, in most cases, 2's complement system mostly use the 2's complement system. Thank you for watching this video.